right, so we had an example earlier similar to this where we were doing 200 grams of a bunch of different metals and just comparing how much electrons were required for each one. We're doing that again, but with some different elements now, so you'll probably recognize this drill if you've been watching every single one of these. So we're comparing aluminum, magnesium, potassium, and iron, and we have 200 grams of each, they tell us. So let's get this organized. I'm just going to make a column for each thing. Aluminum, magnesium, potassium, iron. And for masses, we have 200 grams of each thing. I'm not going to write grams every time. This is crowded enough as it is. I'll put grams over here. Okay, well, we can get a number of moles for each of these because we know number of moles equals mass divided by molar mass, as you're probably well aware. So the masses are all 200, so every one of these is going to be 200 divided by something. For aluminum, the molar mass is 2698, so 200 divided by 26.98 gives me 7.4129. Moles of aluminum. For magnesium, it would be 24.31. Hope I'm remembering these correctly. 8.2271. For potassium, it's 39.10. Is 5.1151 moles. And for iron, it's 5585, if I remember correctly. Just going to check that because I feel like it might have changed a little bit. Nope, still 5585, good. Okay, so 3.5810 moles of iron. So big atoms like iron, it doesn't take as many of them to make 200 grams. Little tiny items like magnesium, it takes a lot of them to get to 200 grams. So the molar mass is the first thing that has an effect here. Those are all our numbers of moles. Let's say moles there. And the next step is, if we have moles of metal, how many moles of electrons does it take to reduce it? For potassium, this is easy because the potassium reaction is K plus a single electron reduces to K. The ratio is 1 to 1, so however much potassium you're making, you need exactly that many electrons. So if you're making 5.1151 moles of potassium, you need 5.1151 moles of electrons. So no trouble there. I'll put moles of electrons over here just to remind us. For the others, though, it's a little more complex because the others have charges of more than one. If you're doing magnesium, your reaction is, because it's magnesium 2, it takes 2 electrons to drag that down to magnesium metal. And so for every magnesium you're making, you need twice that many electrons. So take your number of moles of magnesium and double it, and you get, what is that, 16.4542? I hope, moles of electrons. Iron is the same deal. It's also 2 to 1. Its reaction is iron 2 plus 2 electrons reduces to iron metal. So double this also, and we get 7.1620. And aluminum, the last one, really takes a lot of electrons because its charge is 3. It requires 3 electrons to reduce a single aluminum atom. So however much aluminum you're making, you need 3 times that many electrons. So 7.4129, go into the calculator for this one, times 3 means we need 22.239 moles of electrons to reduce the aluminum. So potassium factory, pretty cheap. Iron factory, still pretty cheap. Magnesium factory, more expensive. Aluminum factory, super expensive. Okay. This is another comparison problem, actually. 4 cells containing, they're all chlorides. We're reducing cesium, silver, silver, lead, and gold. And they want to know if we're taking a current of 5 amps through each of these for an hour, which one will deposit the most? Well, we've got a current and a time, so I feel like the it is funny formula might give us a good start on this. Let's see if it can tell us anything. The current is 5 amps. The time is 1 hour, which is 3,600 seconds. The Faraday constant is the usual. And then we have our number of moles of electrons. So to solve for Ne, we do 5 times 3,600 divided by 96,500. And we get that our number of moles of electrons is 0.186. Our answer only has 2 sig digs, so if I carry 4, I should be all right. 1865 moles of electrons. That should be good. Okay, now I get to do 4 different things with this. Cesium is getting reduced. Cesium only requires a single electron to reduce to cesium metal. Silver also requires just a single electron to convert to silver metal. Lead, they said because it's Cl2, this must be lead 2. So lead 2 plus 2 electrons converts to lead metal. And finally, gold. It's reacted with 3 chlorides, so this must be gold 3. It's not the only version of gold, but that's the one we got. Okay. We need these ratios because these tell us how to jump from electrons to whatever metal we're making. For cesium, it's easy. The number of moles of electrons and cesium are 1 to 1. They're exactly the same. So that tells us we have 0.1865 moles of cesium. Silver is easy also. It's also 1 to 1. 0.1865 moles of silver. Lead is not so easy. For lead, it takes 2 moles of electrons to get 1 mole of lead. In other words, take the amount of electrons you've got, divide by 2, and that'll tell you the amount of lead that you have. So we take our number of moles of electrons, cut it in half, and we get 0.0933 moles of lead. Sorry, tight for space. I'm going to move these over as much as I can to make room for the gold. And for gold, you take the number of electrons and divide by 3 to get the amount of gold. So 0.1865 divided by 3, 0.0622, is it? Yeah, 0.0622 moles of gold. So that's how many atoms there are, but they're saying how about the mass of each of these metals? Well, we can find masses, that's no big deal. The mass for anything is its number of moles times its molar mass. We have all the numbers of moles here lined up, so we just have to multiply each of these by its corresponding molar mass. For cesium, the molar mass is 132.91. I'll write out all the molar masses and then we'll do all the multiplying at once. For silver, the molar mass is 107.87. For lead, it's like 207 something. Yeah, 207.2. And for gold, it's 196.97. Okay, now we do a lot of multiplying. 0.1865 times 132.91 gives us 24. These are only 2 sig digs, aren't they? So yeah, if I round that, it's actually 25. I got 24.78, but to 2 sig digs, it's got to be 25 grams of cesium. For silver, 0.1865 times 107.87 gives 20 grams of silver. For lead, we have 0.0933 times 207.2 is 19 grams of lead. And for gold, 0.0622 times 196.97 gives 12 grams of gold. So cesium is far from the heaviest element. 2 of these are heavier than it, but what really helps it out is that the ratio is 1 to 1 here. Every mole of electrons that you have buys you 1 mole of cesium. Lead and gold are much heavier elements, but this one has a 2 to 1 ratio going against it. It costs you 2 moles of electrons to get 1 mole of lead. And for gold, it's even worse. It's 3 to 1. That's why, even though these are bigger atoms, you ended up getting less mass of them. It's because it takes 2 or 3 times more electricity to deposit a given number of atoms of lead or gold. Okay, what do we have now? 0.2 moles of electrons flows through an electrolytic cell containing molten aluminum oxide. What mass of which product is collected at the anode? Okay, so they're being cagey about which element they're talking about, but we'll soon figure that out. There's an electrode over here. We'll say it's graphite or something. Or no, maybe it won't be able to. If we have aluminum oxide in here, so we have aluminum ions and we have oxide ions, and it's molten, so there is no water. It's just these things. It's too hot for water to exist. The anode, which starts with A, is where oxidation happens. And oxidation is where oxidation number goes up. Well, aluminum 3 is as high as it can get. I've never seen aluminum 4 or 5, so you can't oxidize aluminum any more than this. But you can oxidize oxide ions. You can take it from -2 up to 0. So the only believable reaction that could happen for oxidation would be O2 minus turning into uncharged oxygen. Now, we know that oxygen forms as molecules, which means there must be a couple of these. And we know that if there's a total charge of -4 on this side, to fix that, we need 4 electrons on the right. That all okay? Take a minute with that, just make sure you got that. So they're asking about the anode. Anode's oxidation. Oxidation means the oxidation number goes up, so -2 up to 0. And then I balance this by saying there have to be 2 oxygen atoms on each side, and the charge has to balance also. We know we can balance charge by adding electrons. So now that we know all that, they're saying we have 0.2 moles of electrons. 0.200 moles of electrons. The ratio here is it costs 4 moles of electrons to make a single mole of oxygen. In other words, take your electrons, divide by 4, and that's your amount of oxygen. So if we divide this by 4, we get 0.050 moles of oxygen molecules. And we can get a mass off of that by saying mass is number of moles times molar mass. 0.050 is our number of moles. The molar mass for oxygen is, well, it's 16 for individual atoms, so it's 32 for an oxygen molecule. And what does that give us? 1.6. To 3 sig digs, 1.60 grams of oxygen should come off the anode. And finally, what have they got for us here? In the electrolysis of molten aluminum chloride, So we have our big container. It contains aluminum ions. It contains chlorides. And at the anode, that's where oxidation happens, we have chlorine forming. "20 grams of Cl2. Over on the other side, aluminum is going to form. We're going to have, on this side, chlorine's getting oxidized. On this side, something has to be reduced. Presumably, it is aluminum-3 getting reduced to solid aluminum. So here's our cathode reaction. And they want to know how much aluminum is involved. We could do this with the It's Funny formula. I'm tempted to do this with just flat stoichiometry. I'll do it with the It's Funny, and then maybe I'll show you the shortcut afterwards. Or sorry, no, we won't even need that. We won't need that, or it's not appropriate to use this. Or it's inconvenient to use this because we don't know the current and we don't know the time. We do know the Faraday constant. We can just get a number of moles of electrons without going through this. Yeah, so I'm just going to scrap that and work with the information that they've given us here. If we have 20 grams of chlorine, the only point of having grams is to get moles. Mass divided by molar mass is 20 grams divided by 70.90 grams per mole. 70.90. So we get 0.28. What's happening for sig digs here? My data has 3 sig digs, so I'll carry 5. 28209 moles of chlorine. The reaction that's happening over here, which I should have done earlier, sorry, is 2 chlorides are coming in, converting into chlorine gas and releasing 2 electrons. You can find that in the data book, or you can figure it out yourself just by saying I have to have 2 chlorine atoms on either side, and the charge has to balance. I have to have a total of -2 charge on each side. So, how many electrons is this producing? However much chlorine you're making, you're getting twice that many electrons. So, starting from this, we can take that number and double it and say we're getting 0.56417 moles of electrons. That's how many electrons were pulled out of the chlorine. Well, this is all one big circuit, so that exact same number of electrons must be going down into the aluminum side. So that's how many electrons we have to work with over here on the cathode as well. This same number of electrons. So if we look at our aluminum, on the aluminum side, however many moles of electrons you have, divide that by 3, and that's how much aluminum you get. Only a third as much. So take your moles of electrons, divide by 3. 0.18806 moles of aluminum will be produced. And they wanted a mass. We know how to do that. Mass equals number of moles times molar mass. Molar mass for aluminum is 2698. And from that I get 5.07381, etc. But our data had 3 significant digits, so our answer should only have 3, and that means it comes out to 5.07 grams of aluminum.